This video, we're going to simplify radical expressions. The first topic we're going to look at with simplifying radical expressions is multiplying different radicals together, and then we're going to look at dividing radicals, or if you have a quotient inside a radical, and then we'll actually do the process of simplifying radicals around. So product rule for radicals: if you have a term to the nth root, so like a to the nth root, so the nth root of a times the nth root of b, you can rewrite that as the nth root of a times b. So you have the same index of n, so it's a square root or a cube root. If you have a square root of 3 times the square root of 5, they're both square roots, so you would be able to multiply the inside. So this would become the square root of 15. You just do 3 times 5. Now if it's different, like a square root of 3 times the cube root of 5, those are different. That is not the same index. This is a square root, this is a cube root, so we're not just multiplying the inside. So that's one thing you want to keep in mind. Let's go through some of these examples. So number 1, square root of 3 times the square root of 7. These are both square roots, so we would do the square root of 3 times 7, which is the square root of 21, and then after you multiply, you want to make sure there's nothing that can be simplified, meaning like a perfect square inside. If you're dealing with a square root, like if we had something like this, like if I had square root of 8 as my answer, I can rewrite 8 as 4 times 2, where the square root of 4 is 2. So I'd be left with 2 root 2. But that's not what we're doing right now. Just kind of keeping that in mind though. So the square root of 21, can't do anything with that. Number 2, square root of 15 times the square root of x. They are both underneath the radical of square root, so the index is both 2. So I'm going to do 15 times x, which is the square root of 15x. Number 3, the cube root of 3 times the cube root of 9. So these are both 3's, index of 3, so the cube roots. So I'm going to do the cube root of 3 times 9. The cube root of 3 times 9. 3 times 9 is 27. The cube root of 27, though, we could evaluate, because the cube root of 27 is 3, because 3 times 3 times 3 is 27. So I could take the cube root of 27, so that would be my answer. I don't want to leave it like that. Just like if I got the square root of 4 as my answer, like if I did the square root of 2 times the square root of 2, square root of 2 times the square root of 2 is the square root of 4, which is 2. So I have to rewrite that as just 2. My answer is 2. So in number 3, my answer is just 3. So I took the cube root of 27, which is 3. Number 4, the fourth root of 7x to the third times the fourth root of 2y squared. So they're both underneath the fourth root. 7 times 2 is 14. And then x to the third and y to the second, I cannot multiply those together, so I'm going to leave it as x to the third, y to the second. Then I can't do anything with that at all. So that would be done. I don't have a perfect fourth power there. Like 2 to the fourth power is 16. And 16 doesn't go into 14, so I can't rewrite that at all. So that's just going to be fourth root of 14, x to the third, y to the second. Number 5, square root of 3 over x times the square root of y over 4. So I have a square root of a fraction times the square root of a fraction. I'm going to rewrite that as the square root of 3y, because I could just multiply. They're both underneath the square root. So I could do 3 times y is 3y over, and then x times 4 is 4x. Something interesting happens here, which I don't think the intention of this problem was for this to happen, but I'll just go through this fully. The 4 on the bottom is a perfect square, so I could actually rewrite this as the square root of 3y over, let me actually, so I could rewrite this as 3y over x, and then I'd have 1/2, because the square root of 1/4 is the square root of, not the square root. Erase. Square root of 1/4 is the square root of 1 over the square root of 4, which is 1/2. So I can take out that 1/2. Most problems like that, I don't think that should have happened. I don't think that was intentional. I think that probably should have been like a 5 or something, so then we didn't have any simplifying at all. But that would be the technical answer there. So quotient rule for radicals. Pretty much the same thing, that if you have the nth root of a over b, I could just separate that into the nth root of a over the nth root of b. I can just break it into two radicals, similar to how I just approached that one that's simplified, which I didn't think that was intentional, but we can also do that. So I could separate it into two radicals. So number 6, we have the square root of 25 over the square root of 64. I could separate that into the square root of 25 over the square root of 64. Square root of 25 is 5. Square root of 64 is 8, because 5 times 5 is 25, 8 times 8 is 64. So we would just get 5 over 8 there. That simplifies down to 5 over 8. So I took the square root of the top, square root of the bottom. Number 7, square root of y over 16. So I'm going to rewrite that as square root of y over the square root of 16, because they're both underneath the same index. They're underneath the same radical. So I'm able to separate into two separate radicals. So it's going to be the square root of y, which I can't do anything with, so I'm going to leave that as square root of y, over square root of 16 is 4, because 4 times 4 is 16. So we get square root y over just 4, not square root of 4, just 4, because the square root of 16 equals 4. Number 8, cube root of 27 over 64. They're both underneath the cube root, so I could rewrite this as the cube root of 27 over the cube root of 64. So on top, the cube root of 27 is 3. 3 times 3 times 3 is 3. Cube root of 64 is 4, because 4 times 4 times 4. So we get 3 over 4 for that one. And finally, number 9, I'm going to go up here because I think I'm getting close to my camera. We have the fourth root of 2 over 81 x to the fourth. So let's just rewrite it as the fourth root of 2 over the fourth root of 81 x to the fourth. On the top, we have the fourth root of 2 over, because I can't take the fourth root of 2, over fourth root of 81. That is going to be 3, because 3 to the fourth is 81. So that's going to be just 3. And then x to the fourth, the fourth root of x to the fourth, is just 1. Just like the square root of x squared is x. Square root of x squared is x. And you could look at that a couple different ways. But if it's a square root, that's technically x to the 2 over 2. So that would be x to the first. So you just get x. Same thing here with the fourth root of x to the fourth. That is x to the 4 over 4, which is x to the first. So the fourth root of x to the fourth is just x. So I'm just going to be left with x. The cube root of x to the third, x. Same thing. So we just get 3x for that one. So this answer is the fourth root of 2, because I cannot do anything with that. And then the fourth root of 81 was 3. The fourth root of x to the fourth was just x. So I get the fourth root of 2 over 3x. So let's take these ideas and now let's simplify some radicals. So number 10, simplifying the square root of 24. There's a number of different ways that you can think about this. Like when you're trying to simplify radicals, like you can think of perfect squares. So if you think about 24, what perfect square goes into 24? You can think of it that way. If you're looking at like some complicated numbers, like bigger than 24, you're in the hundreds or 200 or something, it might be hard to find that perfect square. So you can chop things down by 2. Like for example, let me just do this first one and then I'll show you just some thought process. So if I'm looking at 24 is not a massive number or anything where we can't find a perfect square. I know 4 is a perfect square, 4 goes into 24. So 24 is 4 times 6. So using that product rule that we just talked about, product rule is the nth root of a times the nth root of b is the nth root of ab. Well, I can separate it going the other way. So I can have this form and go to the nth root of a times the nth root of b. So what I did is I separated 24 into 4 times 6. So that's going to be the square root of 4 times the square root of 6. Square root of 4 is 2. That's why we just did that. Square root of 4 is 2. So, and then 6 is not a perfect square. 6 doesn't have any perfect squares that go into it. So I would leave that as 2 root 6. But you see that process, though. Thinking about what perfect square goes into 24, that's 4. What you could have also done, I'm going to do this right here. I'm going to erase it though. So if I have like the square root of 24, if you're having trouble coming up with that perfect square, like I said, 24 is not impossible or anything, but let's just pretend it's like a really hard number to find that perfect square. You could just, and it's even, you could chop it down by 2. So this would be 2 times 12 underneath the radical. And then I would have 12. Well, 12 is 4 times 3 underneath that radical. So then I'd say, well, 4 is a perfect square. So I could rewrite that as square root of 4 times the 2 and a 3, which is 6. Square root of 4 is 2, root 6. See how we get the exact same thing? So if you're having trouble finding that perfect square, just start chopping numbers down by 2, or if it's divisible by 3, go by 3. You know, just try to make the number smaller, and then you can start to piece together the rest of it. So don't get into this mindset where you have to find that perfect square. You can find it eventually just dividing by 2 if it makes it easier for you. Cube root of 40. So I want to simplify the cube root of 40. So now we have to think about perfect cubes. So if you don't know your perfect cubes, you might want to review those a little bit. Like 2 to the third is 8. 3 to the third is 27, and so on. 4 to the third is 64. 5 to the third is 125. So when I'm looking at the cube root of 40, I ask, does any of these numbers go into 40? Is 40 divisible by any of these numbers? And 40 is divisible by 8. So I could rewrite 40 as the cube root of 8 times 5. So then I see the cube root of 8 times the cube root of 5. Cube root of 8 is 2 times the cube root of 5. And I can't do anything with the cube root of 5, so I just leave that as cube root of 5. So for number 12, square root of 14, this is 2 times 7. 2 is not a perfect square. 7 is not a perfect square. 14 times 1, nothing. So there are no perfect squares. So the answer to this one is just square root of 14. I cannot do anything with that. There's no perfect squares. Number 13, the fourth root of 48. Fourth root of 48. So now we're talking about fourth roots. These, you don't really need to know a lot of the fourths. This really doesn't come up a whole lot, but 2 to the fourth is 16. 3 to the fourth is 81. And then I'll just write down 4 to the fourth. Like this rarely ever even happens, like 256. And then 5 to the fourth is 625. Like those, it really doesn't get much bigger than that. I mean, it could, but we really usually don't use fourths a whole lot. So I have to simplify the fourth root of 48. I look at my options here of, is 48 divisible by any of these values? And 48 is divisible by 16, and that's 16 times 3. So the fourth root of 48 can be written as 16 times 3. Fourth root of 16 times the fourth root of 3. Fourth root of 16 is 2. And I can't do anything with, I can't do anything with the fourth root of 3. So my answer is 2, fourth root of 3. So I have more examples here that we'll go through, but now these examples are going to incorporate variables and how to simplify those using the rules that we've been talking about. So 14 is the square root of 36x to the fifth. So first of all, 36 is just 6. Square root of 36 is 6. So that's gone. I have nothing left in that 36, because 36 is 6 times 6, so that's just 6. Now, simplifying the square root of x to the fifth. I don't know what the easiest way to think about this is. Everyone has their own preference on how they simplify these variable, like with the exponents. But here's how I like to just think about it. If this is a square root, this is technically written as x to the 5 over 2. Just knowing your rational exponent rules, just that you could rewrite that as 5 over 2. That index is the denominator. From here, you could say, well, 2 goes into 5 how many times? 2 goes into 5 twice. So that means coming out of the radical will be x to the second power, and I'd still be left with a single x on the inside. Because 2 goes into 5 2 times, because that's 4. Then how do I get from 4 to 5? That's 1. So that I still have a single x to the first. So I'd have 6x to the second times the square root of x to the first. Another way to think about this, let me erase that. It's kind of like working with mixed numbers. So like an improper fraction to a mixed number. Where was I? Oh yeah. So if I have the square root of x to the fifth, I could also rewrite x to the fifth in powers of 2. So that would be x to the second times x to the second times x to the first. Because 2 plus 2, let me get my 2 plus 2 plus 1 is 5. So I'm writing these in powers of 2. If this was a cube root, I'd want to write in powers of 3. The only problem with this is it might take a little bit of some time. Like what if it was x to the 58th, you know, something like that, where it could take a little bit longer. But if I just think about it in more just like a visual sense, I have 2 pairs of here. So the square root of x to the second times the square root of x to the second times the square root of x. Square root of x to the second is x. Square root of x to the second is x. Times the square root of x. X times x is x squared times the square root of x. See how we get the exact same thing? So it's completely up to you. I like working with this mix, converting it into an improper fraction and then thinking about mixed numbers and then how I would convert that. So let's try it again. Let's try another one. Cube root of 24, x to the 8th, y to the 6th. So cube roots, we want to think about perfect cubes, and we already talked about 8 going into 24 before. So that's 8 times 3. So the cube root of 8 times 3. Cube root of 8 is 2. So 2 is going to pop out here. So then I still have that 3 on the inside. Now we got to deal with x to the 8th and y to the 6th. So x to the 8th. So I have the cube root of x to the 8th. And I'm going to show you that fraction trick again. So this is x to the 8 over 3. Just using rational exponents. So 3 goes into 8 how many times? 3 goes into 8 twice. That's 3 times 2 is 6. 3 times 3 is 9. That would put me over 8. So 3 goes into 8 2 times. So that means I'm going to have x to the second power come out. So x to the second power is going to come out. So if I went in twice to get to 6, 3 times 2 is 6, I still have 2 left over. So x to the second is going to be left on the inside. Because technically I would have the cube root of x to the 6th times x to the second. That's how that would break down. X to the 6th times x to the second, where 6 divided by 3. 6 divided by 3 is 2, so x to the second. And then I'd be left with x to the second on the inside. Let's do the y. So we have the cube root of y to the 6th, which is y to the 6 over 3. 6 divided by 3 is 2. Nothing left over. 3 goes into 6 2 times. Nothing left over. So a clean y to the second power will come out. Then nothing is left on the inside for the y. So here is my answer. Let's try out 16. Keep practicing this. So we have the fourth root of 32x to the 11th. So the fourth root of 32, so first of all, 32 is not a perfect fourth or anything like that, so I have to use 16 then. So the fourth root of 32 is the fourth root of 16 times 2. Fourth root of 16 is 2, so that's going to become 2, and then left on the inside is still another 2. Because 16 times 2 is 16, fourth root of 16 is 2, so that was 2. Okay, so now we have to do x to the 11th. I'm going to erase this because this is getting a little crowded here. So the fourth root of x to the 11th. Let's do that. I like to use that fraction trick here. So 11 over 4. 4 goes into 11 2 times, because 2 times 4 is 8. So I'd have x to the second. And if you like to think about it as like what is happening with these, this is the fourth root of x to the 8th times x to the 3rd. So the fourth root of x to the 8th times x to the 3rd, 8 divided by 4 is 2, and then you'd be left with x to the 3rd. So let's go ahead and take a look at number 17. So in 17, we have the square root of 18 over the square root of 2. So these are both separate radicals on a fraction, but underneath the same index of square root. So what we can do here is the opposite of that quotient rule, where I can rewrite this as the square root of 18 over 2, where before we had it underneath one radical, we were able to separate it into 2. But this actually helps us out because 18 divided by 2 is 9. So I have the square root of 9. Square root of 9 is just 3. Boom, done. Let's take a look at 18. So there's a couple different ways that we could think about 18. I'm trying to think about what would be the most streamlined approach. It really doesn't matter. So I'm going to take this as 1/2. I'm going to rewrite this 2 here. So I'm just kind of rewriting that as 1/2 times the square root of 20x over 2. Let me rewrite that. So times the square root of 20x over 2. So I'm taking that square root of 20, taking the square root of 2, putting that underneath one radical, and this 1/2 is coming from this 2, because this is technically a 1 over 2, like that. And then 10 divided by 2, or 20 divided by 2 is 10. So that would be 1/2 times the square root of 10x. And then I couldn't do anything with that there. 10 is 5 times 2. 5 is prime, 2 is prime. So nothing happening there. So I could rewrite this as the square root of 10x. Square root of 10x all over 2. So that's 1/2. Then 19, the cube root of 24x to the 4th, y to the 8th, and that's being multiplied by 3, divided by the cube root of 3y squared. So same thing, I'm just going to leave this 3 out to the side. I probably don't need this fraction bar. I'm going to leave this 3 off to the side. These are both, all this is underneath the cube root. So I'm going to rewrite this as the cube root of 24x to the 4th, y to the 8th, over 3y squared. Then 24 divided by 3 is 8, so I have 3 cube root of 8, x to the 4th, just leave as is, because I don't have an x to simplify that with. And then we have y to the 8th over y to the 2nd. 8 minus 2 is 6, so I'll get y to the 6th. Now I can take care of what's inside the radical. So the 3 times cube root of 8 is 2. So the 2 is going to bump out because the cube root of 8 is just 2. So that 3 is now going to be multiplied by 2 because of that cube root of 8. And then we have the cube root of x to the 4th. So simplifying those variables, so the cube root of x to the 4th is x to the 4 over 3. 3 goes into 4 one time, so a single x is going to come out, leaving a single x on the inside because 3 goes into 4 one time being 3, and then one more is 4. Then y to the 6th, so the cube root of y to the 6th, 6 divided by 3 is 2, so y squared. I'm sorry, y squared comes out of the radical, not in the radical. Sorry, that comes out of the radical. So y to the 2nd with nothing left on the inside there. And then that 3 times 2, don't forget about that. That was 6xy squared cube root of x. Pretty tough problem there. 20, last one for this video. This one's definitely a little bit of a challenge question on this video. So we have 4 times the 4th root, 32x to the 8th, y to the 6th, over the 4th root of x to the negative 1, y to the 2nd. So I have 4 times, and then let's just, all of it's underneath that 4th root, so let's just throw it all underneath the big radical here, and then see what happens. So 32, x to the 8th, y to the 6th, over x to the negative 1, y to the 2nd, because it's both of those are underneath that same index, so I could put that underneath one fraction. I'll worry about 32 in a second. I want to first rewrite x to the 8th over x to the negative 1. So that's going to be 8 minus a negative 1, which is 9, because 8 plus 1 is 9. So I'll have 4 times the 4th root of 32, x to the 9th, y to the 4th, y to the 6th over y to the 2nd is 6 minus 2, which is 4. Now we simplify the radical. So the 4th root of 32 is 16 times 2, because the 4th root of 16 is 2. So this is going to, 2 is going to bump out of there. 4th root of 16 is 2. So that's going to be 4 times 2. I'll go this way. So 4 times 2 on the outside. Then we have the 4th root of x to the 9th. So that is x to the 9 over 4. 4 goes into 9 twice, so an x to the 2nd with a x on the inside, because 4 goes into 9 twice, being 8. So 4 times 2 is 8, still 1 left over, so 1x left over. And then y to the 4th in 4th root, that's just going to be a single y coming out. So 4 times 2 is 8, x to the 2nd y, 4th root of x. Tough problem there. I forgot the 2. 2 is still on the inside. 2x, because 32 is 16 times 2. So the 4th root of 16 was 2, but then I still had that 2 left on the inside. So there is my answer. Tough couple last problems there.